Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a real-time collaborative document, the system that lets multiple users edit the same document together with live cursors, presence, and conflict-free merging. We'll cover how platforms like Google Docs, Notion, and Figma keep everyone's edits in sync, resolve conflicts, and preserve version history. Whether you're preparing for a senior engineering interview or building the next collaborative editor, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into designing a real-time collaborative document, the kind of system that powers Google Docs, Notion, Figma, and Confluence. If you have ever wondered how multiple people can type, edit, comment, and move cursors in the same document at the same time without corrupting each other's work, this video is for you. We'll walk through functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building the next collaborative editor, let's get into it. Here is the core problem. A team of 10 people is editing a product requirements document. 2 users type in the same sentence at the same time. Another user is offline on a plane and makes 30 edits. When they reconnect, their changes must merge cleanly with what happened on the server. A 4th user deletes a paragraph while someone else is adding a comment to it. If the system simply uses last write wins, somebody's work disappears. If the system blocks edits with locks, the experience feels sluggish. Users expect live cursors, presence, real-time typing, conflict-free merging, offline support, and version history. Building all of that at scale is hard, and that is exactly why collaborative document design is a classic system design interview. Let's walk through the functional requirements. First, the system must support multiple connected clients across web, desktop, and mobile, each receiving and sending edits in real time. Second, it must synchronize edits with low latency, ideally operational transforms or conflict-free replicated data types, so concurrent changes merge correctly without user intervention. Third, it must provide presence and awareness. Who is currently viewing or editing the document, where their cursors are, what text they have selected, and which user made which change. Fourth, it must support comments, suggestions, and versioning, so users can propose changes, accept or reject them, and roll back to earlier snapshots. Fifth, it must provide permissions and access control at the document, folder, and organization level, including read-only, comment-only, and editor roles. These 5 capabilities separate a toy demo from a production-grade collaborative editor. Now the non-functional requirements. Latency is the most visible one. An edit made by one user should appear to collaborators within tens to a few hundred milliseconds. The system must be highly available, because users are editing around the clock and across time zones. It must scale horizontally to support millions of documents and millions of concurrent connections. Consistency must be conflict-free. Concurrent edits must never produce invalid or corrupt document states. The system must support offline editing, queuing changes locally, and merging them cleanly when the user comes back online. Security matters because documents contain sensitive business data, so transport encryption, access control, and audit logging are essential. And finally, storage efficiency matters because version history and operational logs can grow unbounded. Here is the high-level system architecture. On the left, clients connect through web browsers, mobile apps, and desktop applications. They open a WebSocket connection through a load balancer and a gateway to a real-time collaboration service. Every edit is turned into an operation or a delta and published to an operation stream such as Kafka. The OT or CRDT engine consumes these operations, applies transformation or merge logic, and updates the canonical document state in a document store. The conflict resolver handles offline reconciliation and edge cases. The presence service tracks active users, cursor positions, and selections, broadcasting them back to collaborators. A version history service stores snapshots and the operation log for undo, rollback, and audit. Auth and permissions enforce access control at the edge. The key metrics to memorize: cold. End-to-end sync latency. The time from a local keystroke to the same character appearing on a collaborator's screen, usually targeting under 100 milliseconds. Conflict resolution success rate. The percentage of concurrent or offline edits that merge automatically without user intervention. Active users per document, a critical fan-out metric because broadcasting cursors and edits to 50 editors is very different from 5. System availability, typically 4 or 5 nines, because real-time editing is expected to be always on. Storage per document, driven by the size of the operation log and snapshot history. And version history depth, how far back users can undo or restore. These metrics are what interviewers and product managers actually care about. Let's trace the end-to-end user journey. A product manager opens a shared product requirements document in her browser. She sees 3 colleagues are online. One is in the introduction, another is editing the requirements section, and the third has left a comment on the timeline. She types a new requirement. Her change is sent as an operation over a WebSocket, transformed by the server, and broadcast to the other 2 active editors within milliseconds. A designer who is offline on a train later opens the mobile app. His queued offline edits are sent to the server, merged with the current state using CRDT semantics, and the final document is consistent. Later, the team reviews the version history, sees exactly who changed what, and restores a previous snapshot before the big rewrite. The core models and algorithms. The operation model represents every edit as an operation with a unique identifier. A document identifier, a user identifier, a position or range, the type of change, and a parent version or vector clock. Operational transformation defines transformation functions that reorder concurrent operations, so they produce the same final document, regardless of the order they are applied. CRDTs use data structures such as replicated growable arrays or sequence CRDTs that guarantee convergence by construction. Presence and cursor models track active sessions, viewport positions, caret locations, and selections. Permission models define roles such as owner, editor, commenter, and viewer, often evaluated at the document and workspace levels. Version history is modeled as a graph of snapshots and operations, enabling undo, redo, branching suggestions, and restore. The key trade-off is consistency versus latency. Stronger consistency guarantees usually mean more coordination and higher latency. Now the low-level design deep dive. The operation table is keyed by document and sequence number, storing operation ID, user ID, operation type, position, content, parent vector clock, and server timestamp. The OT or CRDT engine reads operations in a deterministic order, transforms or merges them, and applies them to the in-memory document model. The document store persists the canonical snapshot and the operation log, using object storage for large snapshots and a database for metadata and recent operations. The real-time broadcast layer maintains a WebSocket connection per client and publishes both document deltas and presence updates. The conflict resolver handles offline reconciliation by comparing the client's operation log against the server's log, applying missing operations, and resolving any rare conflicts. Permissions are enforced at the gateway using token validation, and at the service layer using document-level access control lists. For scalability, documents can be sharded by document ID, and presence updates can be batched or throttled to reduce fan-out. Key takeaways for your interview. First, real-time collaborative editing is fundamentally a concurrency and consistency problem, so be ready to compare operational transformation and CRDTs and explain when to use each. Second, always mention the real-time transport layer, WebSockets with long polling fallback, and the challenge of fan-out when many users edit the same document. Third, presence, cursors, and selections are not optional nice-to-haves. They are core user experience and require careful state synchronization. Fourth, offline support and conflict resolution are what separate production systems from demos, so explain how queued operations merge on reconnect. Fifth, permissions, versioning, and audit history are essential for enterprise adoption, so discuss role-based access control and immutable operation logs. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the real-time collaborative document. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the real-time collaborative document. We covered the full picture, from WebSocket real-time sync and OT/CRDT engines, through conflict resolution, presence, cursors, permissions, and the low-level design of the operation pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.